right, everyone. Welcome. Please grab a sandwich, settle down. And welcome at the Interdisciplinary Lunch of AYA today. Before I'll introduce you to our speaker of today, Philipp Tuertscher, let me just tell you briefly something about what AYA actually stands for those of you who are new here, and what the Interdisciplinary Lunch is all about. AYA is the Amsterdam Young Academy, a relatively new platform of 36 young scholars, well, relatively young scholars, from the Vrije University and the University of Amsterdam. We represent a variety of disciplines ranging from, for instance, physics to, for instance, history, my own discipline, and we are active in various fields, science policy, science for and in society, and also we are very much dedicated to interdisciplinary research and making interdisciplinary research work. And that is also how we came up with the idea of the interdisciplinary lunches, and which we have been organizing since September. And those interdisciplinary lunches are intended to create a community, so to support interdisciplinary research, to create a space for conversation on the challenges of doing interdisciplinary work, because there are challenges, and I think we'll hear more about that today. And also to take action on what can be done to foster groundbreaking interdisciplinary work. And I think we can all contribute to that, first of all, of course, by joining lunches in the first place, but also by following the Amsterdam Young Academy at A Young Academy. Twitter, we are very modest, and by sharing our ideas, of course, digitally, but also here. It's my pleasure to introduce you to Philipp Tuertscher, who is Associate Professor of Technology and Innovation at the School for Business and Economics here at the Vrije University. He will provide us today, as I am told, with a theoretical perspective on organizing for interdisciplinarity based on his research. Today's conversation will center on the nature and types of boundaries that may hinder such collaborations. And besides his research, I think Philipp will also draw from his own experience with interdisciplinarity, most notably in Myriad, a multidisciplinary consortium studying biomarker development with regards to Alzheimer's disease and other forms of dementia. I'm very much looking forward to talk. The floor is yours.
So, is this what I promised?
I think so. That's what I was told, but if you change your mind in the meantime, we're very much looking forward to hear that as well.
No, I'm just kidding. I'm very happy to be there here. Thanks for the invitation. I'm at a business school, but I like to study science, and that's been my passion since my PhD. So that's why I'm working with people from a lot of different disciplines. But I was excited to give a talk here, but at the same time also I had a little bit anxiety because I was looking at the video that you recorded by your last guest, by Peter Sloot. It's very, very large footsteps to fill, if I may say so, about all the exciting interdisciplinary work. And I need to, disclose that I do not engage in any interdisciplinary research myself. So I'm not sure how Anastasia or our department head likes to, hear that, because we at KIN group, we say about ourselves that we're a very interdisciplinary group because we have philosophers, we have engineers, we have economists, we have management scholars, sociologists, but the kind of work we do, I wouldn't call it interdisciplinary work. We're all social scientists and also pretty much in organization studies. That's also what I am. So I'm a management scholar, I'm interested in management of technology innovation. Typically, I'm studying not in a business context. Sometimes I do. I study what I like to study, and that's scientific collaborations. And so that's also why I got to study interdisciplinary science collaborations. And that's what I started doing as a PhD researcher by accident, actually. So I was supposed to study a semiconductor company, R&D processes in the semiconductor company, but they had a case of corporate fraud in that company, and I won't disclose the name of the company, but the consequence was basically they shut down all the field access to non-essential people, and I, as a PhD researcher, I was not considered an essential outside contact, so I had to go and look for a new field. And at the conference, at a management conference, I ran into a physicist who's working at CERN, and he's been sharing insights about how they organize as a large scientific collaboration. And that's how I got into this field. Apart from that, I not only study scientific collaborations, but I also do collaborate with a lot of different disciplines. And that is something that I wanted to mention as an example. The Myriade project, so I think I didn't provide all the information. I think you probably picked it up from the website. So I don't have a lot of insights to share about that specific project because it's just about to start. So it's a very exciting consortium. We had our first kickoff meeting. And it's a project which has the aim to accelerate biomarker development. And most of the contribution of this project is interdisciplinary. It's by medical scientists, it's by biologists, computational biologists, which is transdisciplinary per se, anyway, and computer science people. And then we joined that team as a business school, which is kind of funny because we don't expect actually to help them to accelerate that, but we're interested in studying this. So I'm interested in collaborative innovation, how different groups from different organizations, how they can orchestrate R&D processes in a network. And that's something that's also very important for corporations, but we can also observe it in science. And it's much easier and much more fun as researcher to study in a science context, because very often it's much less cynical, it's much easier to get access and to observe actually the dynamics of how you share and integrate knowledge across disciplinary boundaries and across organizational boundaries. And that's what I've been studying mostly in a lot of different settings. I've been studying this in science collaborations. It's what I started as a PhD student and still love to do. I've studied it in open source software projects. It's also similar. You have people who come with very different backgrounds and purposes, and they team up in a open source software collaboration, and you have similar challenges. You have people who don't have their motivations and incentives aligned. You don't have a common source of funding, and so a lot of also challenges of collaboration across boundaries. In online communities like Wikipedia or other types of user innovation communities, you can observe these kind of things. Crowdsourcing, also something, in particular collaborative crowdsourcing. So that is, I guess everyone is familiar with crowdsourcing, but very often it's just like unidirectional, that people are submitting ideas, post ideas, and those are then assessed and evaluated by companies, and people can win something then. But what we are interested in is to study collaborative crowdsourcing, where people disclose their ideas and others then comment on those ideas, bring their perspectives into the ideas, maybe merge two similar ideas or complementary solutions. And there's a lot of very, very interesting dynamics also going on. And again, we have these boundaries, sometimes cognitive boundaries, because people are coming from different perspectives sometimes, but also motivational boundaries. So what I wanted to do today, because I tend to talk a lot, but I also wanted to engage in a conversation, I just wanted to run through a couple of sites and just to throw out a couple of ideas that I came in touch with in my own research, but also research by colleagues about interdisciplinarity. So first I wanted to talk about some of my research that I've done about the scientific collaborations at CERN. And what I've been interested, sort of phenomenon that fascinates me most is how is it possible to accomplish knowledge integration? That's something that's very, very difficult, and it's also something that's in our field is very much understudied. Knowledge integration is not just adding, different data and aggregating data, but knowledge integration is a process of a synthesis where you have two different ideas that somehow are incommensurate, and you are integrating those ideas into a solution that's more than the sum of its parts, essentially. And that is the difficult process in small teams or in a dyad between two individuals, but it's all the more so difficult if you have a large organization and you have different teams. And so this is something that I've been interested to study at the ATLAS experiment. That's one of the two large experiments at the Large Hadron Collider at CERN in Geneva. So I'm not sure if we have any high-energy physicists here in our group. So let me just briefly explain. So this is a big particle detector that's observing what happens when two proton beams collide. And the purpose of this experiment is basically recreate what happened at the Big Bang and to study some subatomic phenomena that are difficult to observe in nature. So this is the experimental setup, and this detector is like a digital camera, you could say. It's just much larger. So this device is about 50 meters long, is some 30, 40 meters high, weighs 7,000 tons. It's incredibly complex. You see it's built like an onion, different layers of technologies, and has a lot of different detectors. Some of them use electronics that basically need to be built in such a way that they use hardly any matter because they're not supposed to interact with those particles. Then you have other type of detectors that need to use liquid argon, so that's liquefied gas that need to operate at very low temperatures. You have some other detectors that use very, very thin gold wires that are in vacuum tubes. So a lot of different technologies, and although all this experiment is a physics experiment, so it's unidisciplinary in a way, they need a lot of people from different disciplines in order to help them to build the components. So there's a lot of different flavors of engineers, material scientists. You have, well, most of them have some connections to particle physics, but in a way, they have these different backgrounds, their different specializations and expertise, and this is not just a very, very complex technological system, but it's also a very large collaboration. So I'm sorry you cannot properly see it, but it's a collaboration. So here on this picture is about 500 people, but it's actually, the whole collaboration involves about 3,000 physicists from 150 different universities scattered all over the globe. And the question is, how is it possible for them to coordinate their different R&D or development tasks and to integrate, to synthesize the different specialties knowledge. And this is just an analysis of a co-author network that I've done over a period of about 15 years of this collaboration. And that was just an exercise for me to play around to identify hotspots of interactions in this collaboration. And through the color code, the temperature indicates the time. So what you see is you have this very, very complex collaborative network, but you also see that different points are getting more or less active at different moments in time. So this is a very, very dynamic organization. And what's very interesting is to understand how they organize and how they're able to orchestrate this whole development process. So it's a complex device, but it's also a very, very complex social enterprise. I need to say I've been very much humbled about the very amazing people that I've been interacting there. So one of the leading scientists in the collaboration, he told me very much in the beginning, if you want to understand our science, you need to understand our collaboration. But if you don't understand if you don't understand the science, you don't understand the collaboration either. So it's basically, you need to have an appreciation of the technical intricacies, but you also need to be very, very sensitive to sociological processes going on. Now, what we did find in this collaboration, what was really key is, of course, you need to have something like a common knowledge. So that's something that Peter Sloot, I think, also emphasized. You need to have common knowledge, you need to have common language also. You need to have shared space. You need to have shared devices, instruments, or methods. And that is something that we in our field, we call it a boundary infrastructure. So this is an infrastructures of objects and resources that facilitate the interaction of the scientists across the different disciplinary or specialties boundaries. But it struck me that there was also a question, I think, from the audience last time in the last meeting. So isn't there a trade-off between this, the T bar, this very, very broad disciplinary knowledge, and don't you have to have also specialty in your own discipline? And I think that was a very, very well taken comment, because that is something that's really essential, because if you only have this common ground, it's a sine qua non, but you need more than that. What we found is also you need more also than this common ground plus your own disciplinary knowledge. What you need to have in these collaborations is you need to have what we called interlaced knowledge. And now the clicker doesn't.
There's a pop-up.
Okay, thank you. Oh, no. Yeah. So you need to have decentralized knowledge overlaps across the different groups. And this is a phenomenon we call interlaced knowledge, because it's interwoven like a web. And it's something a little bit difficult maybe to think about without a representation. But what we've done is we have studied people who have been co-authored or collaborated on different sub-projects, and we have tried to tease out their different specialties and also where they developed additional specialties. And we did so by doing natural language analysis of the papers that they have co-authored. And by studying that over time, we could see how people were developing expertise in areas of colleagues that they collaborate with in interdependent components or technological areas. And over time, we could see that a lot of people were developing overlaps with these other areas. So they become experts or specialists in multiple domains. So not just their own domain, but multiple domains. Now, what's very interesting is this is something that happened organically. It happened in a decentralized process. And what we found was we found different topologies, different kind of network structures of the knowledge structure of these collaborations. It's very nice. These collaborations had a lot of different sub-communities. So we were looking at different components. So for example, there's the calorimeter. That is something that's pretty much in the center of the device. And then there's the muon spectrometer, which is something that's at the outside. And so the outside devices have much fewer interactions than the inside devices. So we were running this analysis, and we could see indeed, if you're looking at this network representation, you see much fewer links. And the links are interconnections. That's based on a covert analysis of different domains, of different topic areas. And if you compare that to this calorimeter, you have much more connections. And basically a network with much more connections and also random connections, that means redundancies. And such random connections in a network topology also means you have fewer bottlenecks in a network, you have fewer opportunities to find workarounds, bypasses. So it's making a network more robust. And we found also that something that was the result of this interlaced knowledge structure. It made the whole enterprise much more robust because they had a lot of backup solutions that they could fall back on when one of the solutions turned out to be not feasible. Also, when a person from this very large collaboration, which had very permeable boundaries, suddenly stopped to be member of the collaboration and newcomers came in, then there were still some redundant expertise overlap from the remaining people. So that made essentially this collaboration very robust. Now, we were interested in understanding how this comes about, this interlaced knowledge. And basically it was part of these common forums, these shared spaces in which people interacted. And what was very interesting is the way that they were interacting. So these were forums of contestation and justifications where people engaged in a scientific process, having a debate or an argument about competing ideas, competing proposals for technologies that they could use for component X or Y or whatever. And what's very interesting, one of the scientists explained this like a tribunal, like a procedure in court. So basically what they were doing, one party was presenting its case, then there was the opponent party presenting their case, and then they started to look for problems in the other approach and to start to ask nasty questions that would be very challenging and difficult for the others to offer a rebuttal to. So it's very similar how we do in a review process. So what's very important here, in this process, scientists try to identify weaknesses in the other technologies, and in doing so, very often they reflected about possible weaknesses they would have in their own designs. And since this is a very, very interdependent system, where maybe you have a very, very great solution as a standalone, but it may have negative implications on other components, so the approach to beat the opposing technology very often was finding weaknesses, negative spillovers of the competing approach on interdependent subsystems. So that way, that is how we found that people basically decentralized. They were looking for connections, for knowledge overlaps that were of relevance to their own subsystems, to other subsystems. So this is how, in a very, very organic dialectical process, this interlaced knowledge was forged in a collaboration. Now, what's very interesting here, this is not just understanding what others are doing, but what's also very important, this is knowledge of what, how, and why. And I think that's also something that that's very important in interdisciplinary collaboration. Not just to understand what others in another discipline are doing, but you also need to understand the underlying assumptions, their frameworks, their motivations, why they do things in a certain way. Because that then allows you to understand what you need to change or what you need to tell them if you want to engage in an interdisciplinary collaboration with them. Yeah. So I also wanted to throw out another idea, which is not based on my own research. And that is, there's these cognitive boundaries, and I think what I've been talking about that falls into this category of cognitive boundaries in interdisciplinary collaborations, but you also very often have political boundaries. So the cognitive boundaries is basically that you lack the shared language and methods. Basically, different disciplines very often are at odds, or their assumptions are at odds. So that's one sort of boundaries. But other challenges, other barriers are of political nature. So this is how we as science are organized. We are caught in silos. We have funding and organization and structures and hiring, promotion. Everything is organized by departments and typically very much in different disciplines. This, by the way, is also something that at CERN, they very much experience as a big problem. Because in this experimental physics, very often people are doing interdisciplinary work. So very often they're publishing technical papers together with engineers. And that is something that by fellow physics colleagues at their home institutions very often is not highly rewarded. So especially if you have a small physics department with theoreticians, with small labs, but then also experimentalists who are in these large collaborations, then the kind of papers that they very often publish in addition to the large discoveries, they don't count that much. So there's a discount on this technical and interdisciplinary paper that they write with computer scientists, technicians, so on and so forth. It's less of an issue if it's in one of the large labs like Fermilab or there everyone understands, what interdisciplinary research entails. But if it's really in a typical traditional physics department, then they might run into those sorts of issues. So there is a very, very nice paper by colleagues who have how organizations in nanocenter initiatives can overcome these boundaries. And they found two types of shared objects. I'm going to say in a minute that the shared objects sounds a little bit cynical maybe, but essentially it's a shared technical infrastructure, shared instruments. They're very important to overcome this both cognitive and also the political boundaries, because they enable new research questions and discoveries in different fields. And therefore, these instruments, the availability of these instruments, very often is like the glue between different fields. So you have, for example, new types of microscope that are useful for chemical scientists, and then they team up with people from these nanoscience centers, for example, because they need those people in order to understand how those instruments work. So this is like the cognitive boundaries those instruments help to overcome. At the same time, a lot of those instruments are shared. They are bought together. You are using common funds. So that means you make projects, or are more likely to use to create projects with such nanocenters because you have the instruments available and you don't have to buy them yourself. You also maximize the utilization of these instruments if a lot of outside parties come to these nanocenters as hosts and use those instruments. So this is how the instrument itself, the availability, provokes collaboration. Which otherwise people from the same universities would probably not engage in. Now, the other kind of shared resource or objects that they found very important is the role of students. So, I don't want to label students of objects, but they are the catalysts. And they're vital. And the students also, at the Atlas collaboration at CERN, they are a majority of the collaboration, or a large part of the collaboration. So in the Atlas collaboration of these 3,000 scientists, it's about 1,000 of them are students, master and PhD students. And that's very important because students, on the one hand, it's much easier for them to overcome some of the cognitive boundaries. For students to learn a new technology, they don't have the legacy of the old technologies, so it's very easy for them sometimes to become literate in two disciplinary languages at the same time. The other thing is to overcome political boundaries. It's also very important because students have very low opportunity costs. They have relatively low risk. You could say you have nothing to lose. On the other hand, you have also a lot of things to win. And what it turned out in this study was that actually it is the interaction of the students and the experiments which is creating this symbiotic relationship that is facilitating interdisciplinary collaboration. And they had a very, very nice model, and you can look that up in their paper, Kaplan, Milde, and Rowan, and Academy of Management Journal. They identified a couple of very, very nice symbiotic practices that they labeled it. And just to show you some examples, so a student can have an interest to see both languages, both communities, and so they facilitate interdisciplinary work. So that's something that we, I need to be honest to myself. It is something we are caught in our own rhythms, in our own communities. It's very difficult for us to escape those. It's much easier for students to engage in this role and become a facilitator to bridge these disciplinary boundaries. When it comes to working with specific new devices, very often what happens is that the student becomes an expert to use a new instrument in a different way. So there's a co-specialization between this interdisciplinary student and an instrument. So, for example, what they found here, and also what this quote says, is, so although a professor may be very versed and experienced working with microscopes, there may be instruments by different manufacturer that have, certain differences, subtle differences, that would take quite a while for the person to really understand, to use it in the proper way. And a student can become the key resource and the expert, and also the to-go-to person in order to handle this. And then also students very often, they forge the connections because they identify there could be a supervisor from a second discipline that they can leverage. So for a student, it's a win-win situation because the student gets double feedback, double input, and also the student can develop a new line of research for himself and build a career based on that, which of course would also be possible for a professor, for a faculty member, but that person typically has much higher opportunity cost and much more at stake in case it doesn't work out. So that's it in a nutshell. I promised not to take too much time, so I hope it did work out. So we can talk about this now.
Thank you very much, Philipp, for a talk that I think complements the last contribution very nicely in highlighting both the role of scientific networks and also the way in which knowledge develops within those networks. But before I ask any questions myself, I would like to ask the audience if any questions have popped up.
I actually partly wonder if it's true that the risk is lower for students. Because if I take now 2 years to do something interdisciplinary and I harm my status, they're not going to demote me or anything. I have my tenure, I have everything. So I kind of have the feeling that I have less to lose to take a risk, especially for 1 or 2 years, than my students who have to find, if they want to stay in academia, a job afterwards. So if this new field doesn't work out, they might be empty-handed. So I wonder if it really applies.
Yeah. What constitutes a risk, that very often may be, subjective or depending on a certain situation. But students, they haven't built a career yet, and so they also cannot, lose that career. But the other thing is also students have not built a career that brings along with it some expectations. And you as a faculty member, you have certain expectations to do some work in a certain area maybe, or you're part of a group that has a certain infrastructure and stuff, and you're expected to also make use of that. That could be reasons why you have an opportunity cost, or it may not be so easy for you to engage into some, different work. But the other thing is also how people perceive risk. So students are new. Very often you could also say, like entrepreneur, they are more naive, and try out, long shots or riskier projects. I guess that's how I would answer this. I mean, this is something students in this Nano Center, very often they were daring to make connections or to introduce faculty members in doing new collaborations. Also taking up the task of doing a lot of the learning and also moderating and maybe sometimes also managing some of the tension between the different faculties or faculty members. That's something that without the students would be very, very difficult to happen. Maybe also, I not necessarily want to, maybe risk is also a wrong word if you think about it in terms of, job security or stuff like that. I mean, then obviously if you're a student, you don't have a position yet or so, and you compare that to a tenured person, that's something else. But if you're thinking about the reputation and the expectations that you have, and also the opportunity cost of the other kind of projects you could engage with and be productive in the meantime and get papers out that are counted in your field, that is something that I think there is a difference. Let's not say which one's higher, but it's a different nature, and so you're also more likely to engage in a different set or different kind of projects.
Yeah, I do think it's a different nature, and I do see your point, but especially for the publications, I still feel that the risk for my students is higher, personally.
But we have students in the room, so maybe you
Yeah.
guys can share.
And it might also depend on the field.
Yeah. What they found here in this case, the students very often they had more. Students very often they were not yet. They had not yet opted for a certain track. So they had publications sometimes then in 2 different fields or disciplines. And for those students, it was perceived as real options. Very often also, for the students, they have a chance that a new field or a new tradition is going to emerge. And then they can, develop a signature and a profile in that field. And for them, it's an opportunity. But for someone who's already established in his own field, creating that new profile may not be that valuable, may even be counterproductive for that person relative to the reputation the person already has developed. But where do we have students? What do you think about that?
I mean, I do see, rather than risk, rather than being naive to the risk, I do see that as being like having boldness because of necessity. So rather than not understanding what could be the risk going through that process, we have to accept that process of pioneer what could be hybrid or new.
Yeah, but think about the risk also, not just the risk in getting a paper out or being successful with the project. Think about the risk also about university politics. That is something that a student who is more or less an outsider and is not yet on the different boards, that's something that a student probably can use the newness and wanting to try out something new as something that's making things easier.
And also maybe if you broaden the concept, so maybe risk is, like you said, the optimal word, but if you think about the cost, then you also start including path dependency and inertia, then of course students will be more malleable in terms of what they can learn and which field they can contribute. So it's risk, but then also like what cost.
I agree with Anke that it's rather difficult. You have to be careful that you don't get 2 captains on the same lesson. And the student becoming this like instirable boat and doesn't know where to go to. But one advisor wants to go to the left, the one to the right, and you end up somewhere nowhere.
Yeah.
So there's still a large responsibility for this one person, one advisor to become the real captain to guide it.
Yeah.
Into success. I think there's a difference between master students and PhD students. For master students, you can do it's a bit more free-form research. And what can they use? Okay, they don't need to get 7 or something to report whatever methods. It's overcomable. But for a PhD student who committed to a project for 4 years, you also want to really learn something. Yeah.
Yeah. Now, in the center that these studies, our colleagues, it was so students, it was PhD students and postdocs that they used. Now, it totally resonates with me what you say, but this is not just an issue with interdisciplinary collaboration. That's also an issue if you have large supervisor teams within the same field, right? So that's a kind of the same problem.
But here also for CERN, it's so big that you get all the advantages. Right? If you set up your own small interdisciplinary team, it's much more difficult to profit from this interdisciplinarity. And if you are in a scheme already 50 parties or 50 universities are collaborating, so it's not that you have to set up yourself this interdisciplinary collaboration, it kind of exists, and in that environment you can invite the student to exploit it.
Yeah, well, what I found very interesting in CERN, of course, you have all these people with different specialties based at CERN, but then these collaborations, they are like visitors to CERN. So this is kind of also a little bit confusing. So you could imagine, the Large Hadron Collider is like the racetrack, and then you have Formula One that comes with its teams to do this experiment. And then, of course, you have overlap because CERN itself is a large institution, and CERN is one of the 150 research institutes participating in this collaboration. And it's right, you have a large variety, you have these different disciplines, but also, so what we observed is very often the students, they don't come into a setup structure or organization. It is actually very relatively loose networks. Also, what we observed in this collaboration, there was no one-to-one mapping of institutes to different components. So there's also different ways of organizing. The sister experiment, for example, that was organized in a different way. Basically, there were different institutes or group of institutes. They committed to provide in-kind contribution, and then basically they had everything ready, planned, and a lot of components pre-assembled, and it was more organized in an industrial way. So this here was a much more messy process where people basically, they self-selected, like in an open source software project, based on what they find interesting and where they think they can make a contribution. So very often they would team up not with people from their home institution, not even with their supervisor. Very often they ended up getting a responsibility because they had a thing, they had an interest for, you know, one of the detectors had to have very, very clean metal components. So there was one of the students who went into metallurgy, which none of the physicists would have done. So, I mean, that is something, there is a relatively low cost for the students to go into this new domain, because the student is not yet invested into something else. So it's easy for that student to build a new career. I think what Bomi has said, this path dependency, is something that's relatively important, because once you have created your profile, it's not so easy for you to deviate. You know, it's diluting your profile. You are well known and established in your domain. You also you are more productive and efficient working in your domain because you understand it very well. So what very often happened, that it was rather junior people who became the experts in some of these settings. Of course, they need to work then together and collaborate with more senior people, because they have then the big picture. But that's the very, very interesting thing here, that you have a lot of self-selection going on. And I think that's also very important in such an interdisciplinary collaboration, because very often you have new discoveries, new insights by accident. And you cannot plan and organize for those. So you need to organize for serendipity. And that happens much better if you have a decentralized mechanism.
We've had a couple of questions now with regards to the role of students and what they have to win or lose. Some other themes also came up, the role of interlaced knowledge, cognitive political boundaries. Are there any questions about those kind of? Yeah.
Did you make any observations on how each discipline itself thought about interdisciplinary research?
Well, it's funny, at CERN they were not considering themselves as interdisciplinary at all. They all considered themselves as physicists. The only people who were really suffering from that were the engineers, because the engineers typically they were considering themselves as, you know, master of things. They were able, you know, a lot of them, they have worked before in industry, aerospace or stuff like that before they moved into this project. And they used to be, you know, better than economists and managers and stuff like that. They were like at the top of the food chain. Then they came to the physicists, and physicists asked the engineers to help them to build stuff. And engineers, they had quite to struggle with the fact that physicists never accepted anything for an answer. So, for example, there was a very frustrated cooling and ventilation engineer who had to. I was telling about these cryogenics. So some of these systems had to operate at 3 Kelvin, and then some other systems that are just adjacent had to operate at room temperature, some electronics. And so you have to get a lot of heat out of a system in order to not interfere with this cryogenic, with this liquid argon. So cooling and ventilation, that's very, very important, but getting out temperature means you need to have a certain cross-section of a pipe, for example, or of a cooling channel. And engineers, typically they work with their experience, their rule of thumbs. So if you need to get out, such and such energy, then they look up their tables or, rules of thumbs and then say, well, you need to have such and such a diameter. And if they would do that for a corporation, for a building company or anything, like that, then people would just accept that answer, accept that that's based on, experience. But physicists said, no, we can't have it like that. And then the engineer said, well, you have to have it like that. And the physicist says, why? And that's the moment then when the engineer started to struggle, because they didn't have an explanation other than, well, because that's how we do it. Well, the engineer was telling us a story how he had to go back to his books to look up the formulas, then to explain the physicist. The physicist took the formulas. 2 hours later, he came back and said, look, based on my calculations, it should be possible, to do it with less and stuff like that. So there was physicists, but the physicists, they were kind of very, very broad and went into engineering, they went into metallurgy, as I said, they went into material science, they had to go into optics. So a lot of different specialties. So they didn't really consider themselves as different disciplines. Now, we also studied as part of this project, this was from the National Science Foundation funded this project. We were from the US, we were also studying a collaboration that was a truly transdisciplinary collaboration. It was from the NIH funded. There was a series of transdisciplinary tobacco use research. So that is economists, health economists, behavioral scientists, life scientists, people who were studying tobacco use, addiction, the implications on the health system, cancer, so on and so forth. The funny thing was there, everyone was labeling stuff as interdisciplinary or transdisciplinary research, but actually people were not changing their behavior of the actual research that they were doing compared to before that grant application. And so that's also something that we observe. So, I mean, sometimes you have political boundaries that prevent interdisciplinary work. Sometimes you also have political, how should I say, attractors to do engage in such interdisciplinary projects. But then the question is, does the treatment actually create the desired outcome? And what we found here in this setting, very often, it did not happen. And that's partly because we have, well, much deeper institutions. The way the fields are organized, the ways that universities are organized, the ways our publication outlets, the journals, the review process is organized. By the way, one of the papers that I've been trying to publish from the work on CERN, I've been struggling a lot because I don't get it accepted in our field, in management. It's very, very difficult because some of the assumptions that managers or economists are taking for granted, such as profit maximization, that people do something based on individual motivations, that is something that is like switched off in our setting. Because scientists, of course, they also are motivated, but they have very different sets of motivations. And some of these motivations, they follow different mechanics. So there's people who are studying the economics of science, but economics of science are very, very different. So you don't have monetary incentives. Our currency is publications or citations, but it behaves very differently. And so it also, the way it influences our behavior is very, very differently. Another thing is also the way that value can be captured or appropriated here in this setting is also very different from how it works in organizations. So what do you think the deal about authorship in this collaboration, in this large scientific collaboration?
What do you mean the deal? What do you mean, what's the question?
How does the collaboration decide about who's an author or not an author on a certain paper?
Consortia or the whole research group?
The whole research group, the whole 3,000?
Yeah, or subgroups.
Yeah.
Just like a large body of people.
Well,
A single famous paper from the Higgs boson is 1,500 authors or so?
Well, it depends on when it's been published. I mean, the Higgs discovery, I think that must be like more than 3,000. But it's like it's a few pages of the paper, and then it's like 20 pages of authors. Yeah, yeah.
Then you can't find an independent reviewer.
It's the whole. It's a whole collaboration, and basically they have two motivations why they do it like that. First, they say if we would really to look into who's done what, we would be so busy keeping track of those things that we wouldn't have time to do the actual science anymore. That's part of it. The other thing is also it would create adverse incentive and it would break up the collaboration. Because there's a lot of mundane tasks, such as taking shifts. You know, these experiments, they run 24/7 for a couple of weeks, and you don't know when something important is going to happen. And some of the things need to take immediate action. And so it may be a postdoc who is a shift leader, and it's something that's most probably not very important, but it could be very important, and you don't know. Even if someone is a technician and he drops a screw, you know, or leaves it in there before the magnet is switched on, you know, it could ruin the whole experiment that has cost €1 billion. So basically they say, you know, even the smallest thing is essential for the experiment, and it's important that people are taking it with care. So therefore, the conclusion is everyone deserves to be an author.
So is they including everyone?
They're including everyone. So that also has a lot of implications. So, you know, if you go to a job doc and you are an author of a paper that has 3,000 co-authors, how do you explain what is your contribution? How do you explain what it is that you've actually done? So that's something that may be very, 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 yeah, you didn't drop the screw, yeah. But that's something that's very, very difficult to understand by some of the people. It's no big deal if you are, you know, joining one of the large high-energy physics groups, because they know how it works. And they have replacements for this, so there it counts if you're in charge for a component or for a team or something, if you are sent by the collaboration to give a talk, so that's also very interesting. The talks, basically you come as, you speak on behalf of the collaboration. It's also very funny, the chief scientists of this collaboration, his title or her title, it's a woman at the moment, is spokesperson. So it's not the PI, or it's not the president, or it's not the, you know, chief something officer. It is the spokesperson, so the person that speaks on behalf of the collaboration. So that shows the different kind of mindset, how this collaboration works.
I think there's room for one last question. I think you raised your hand.
Yes. So to overcome the political and cognitive barriers, one of the most important things is material, or the Hadron Collider. Do you see any parallels to research fields where there's no use of material, for example, like in social sciences, or
well,
something where you cannot really develop?
Yeah, I think in the social science we also have research sites. So, I mean, that is something if you have an important research site. You can also think about, you know, large surveys, for example. You could think of also a research infrastructure. So, yeah, for entrepreneurship and innovation management, for example, there is this community innovation survey, which is a survey that a collaboration of innovation and entrepreneurship scholars in, I don't know, dozens of countries are populating every year and are creating a very, very large panel, which basically in each country or in each region is administrating the same kind of survey. And then people are pooling together the data, are sharing the data in order to replicate studies or to have longer term panels, also to start to think about new research questions. And I think that is something that you could use also as a kind of analogy. So it may be less material, but it's also a kind of a shared, a common infrastructure that you use. Also in, I mean, in other science, if you're looking at neuroscience, where you need to use medical imaging technologies, for example, it's not just the instruments themselves that are the shared common resources, but it's also the images for example, the data that you need to pool, or also the protocols that you need to negotiate in order to make data shareable, exchangeable, and reusable by others. Also procedures to ensure compliance with privacy and data management and stuff like that. That's all stuff that I would also count to research infrastructure that can be shared in a scientific community.
Thank you very much,
You're welcome.
Philip. Until I came here, I was very happy that last week I managed to solve a potential issue of co-authorship with a colleague of me, and now I have to reconsider whether that's actually an achievement. Thank you very much for a very illuminating talk. Thank you all for being here with us today.